Guys, and welcome to a new video. In this video we are going to solve an integral on the complex plane. So we are going to calculate an integral considering the residual theorem. Okay, so the integral we are going to solve is the following. Integral from 0 to plus infinity of 1 over x raised to the power of 4 plus 1 dx. Okay, so in this case we basically have an integral with a real variable. X is a real variable, but we can basically calculate this integral considering an integration on the complex plane. So the idea is to consider basically a correspondent integral on the complex plane. So we have to consider an integral of a complex variable, let's call it z. So we have to consider this integral of this analytic function where we have, as we said, the complex variable z, and the integration is along a path c. Okay, so now we have to consider a let's say a good path c such that we somehow end up with this same integral. So here the idea is to consider c such that is given by a straight line from minus r to plus r, and then we have also to consider the set of complex number z, so z belonging to the complex plane, such that the modulus of z is r and the imaginary part of z is positive. Okay, now I'm going to draw C so that maybe it is more clear. It is clear what we mean by this characterization. So basically we, as we said, are on the complex plane. So we have the horizontal axis, which is which represent basically the real part of the numbers, and the vertical axis basically is for the imaginary part of the numbers. So as we said, C is given by this path on the real axis, so we have to consider minus r and r here. So we have to consider this straight line from minus r to r, and this set of numbers are basically constitute a semi-circumference. So the circumference is basically this, where, as we said, we have the set of numbers z such that the modulus is z and the imaginary part is positive. Consider a positive orientation, which is a counterclockwise orientation of this kind. So we are basically claiming, we are basically saying that we have to consider the integral along this path of this analytic function. Okay, so since C is made up of this straight line and this line, we can say that this integral, so the integral from minus r to r of the function plus the integral along this path, along this semicircular path, which we can call CR, for example, of the same function. Okay. So now the idea is to resort to the residual theorem, and this theorem basically claims that this integral, so the sum of these two integral, is given by 2 pi I times the sum over k of the residues of the function f, and we call the residues zk. Okay, so basically we can calculate this integral, so the sum of these two integral, just considering the sum of the residues of the function zk, and these numbers zk are basically the numbers such that basically this function is not defined. So first of all we have to find these numbers. Okay, so to do so we basically have to consider the numbers plus 1 is 0. Okay, so because for these values this function is not defined basically. So here we know that this z raised to the power of 4 is minus 1, and this equation is basically the solutions of these equations. Of this equation are the numbers zk, such that that we can also write rho k times e raised to the power of I theta k, such that zk to the 4 is minus 1. So we can write that zk are those numbers such that rho k is just 1, and theta k is 1 plus 2k over 4 pi, because we know that minus 1 is e raised to the power of I times pi plus 2k pi, and here we have 4, so we basically end up with this equation. Okay, so we have these values. The modulus is 1, and the phases are this one. So k is obviously a number which is 0, 1, 2, and so on. And so because of this we have to consider theta z0, which is just pi over 4, and then we have theta 0, sorry, is pi over 4, and then for example pi 1, theta 1 is given by 1 plus 2 over 4 pi, so is 3 over 4 pi, and then we have theta 2, which is 5 over 4 pi, and then we have theta 3, which is 7/4 pi. Okay, so these are basically the 4 phases of the 4 poles of the function. In fact, we know that this equation has just 4 solutions, so these are the phases of the 4 solutions. We can write that z0 just 1 plus I over 2 under square root, because we know that z0 is, as we said, e raised to the power of I pi over 4 pi over 4, sorry, and then this is cosine of pi over 4 plus I sine of pi fourth. But we can also write this, as we said. Okay, so this is z0, and then we have, for example, z1, which is minus 1 minus I over 2 under square root, because we know that z1, as we said, is e raised to the power of 3 over 4 pi, and then we have I, obviously, but we can also write this. Okay, and then we have also we would have also theta 2 and theta 3 for z2 and z3, but actually here in the residual theorem we have to consider just the poles zk that are basically inside this path, inside C. So we have to consider just z0 and z1, which are two poles that have a positive imaginary part. Okay. Okay, so here we have just to consider these two poles, which are simple poles. So now we have basically to consider the residue of these two poles, and we know that, for example, the residue of the function f of our function for z0 is given by the limit of z approaching z0 of z minus z0, and we have to multiply this term by f, but we know that f can also be written, since f was 1 over z to the 4 plus 1, we can also write this with the solutions, basically. Okay, and z minus z3. Okay, where z0, 1, 2, and 3 are the 4 poles. And now, if we consider this, we can cancel these two terms, and then we end up with the limit of z approaching z0 of 1 over z minus z1, z minus z2, and z minus z3. Okay, so here we basically end up with 1 over z0 minus z1, z0 minus z2, and z0 minus z3, and this is the residue of z0. Okay, so now we basically have to put into this result the value of z0. You put in the value, you basically end up with the residue of the function f of z0, which is minus 1 over 4 times 2 under square root minus I over 4 2 under square root. Okay, so this is the residue of the first pole z0, and the residue of z1 is, if you do the calculation, is 1 over 4 2 under square root minus I over 4 2 under square root. Okay, if you calculate the two residue, you should end up with these two which are inside our path, you should end up with minus I over 2 and 2 times 2 under square root. Okay, so now, as we said, basically the integral of our analytic function along C is given, as we said, by the sum of these two integrals. Okay, and we know that, as we said, this from the theorem is given by 2 pi I, and the sum of these two values, which, as we said, is this one. So we have minus I 2 and 2 under square root, and here we basically end up with I plus I times I is minus 1, and then we have these 2 and 2, so we end up with pi over 2 under square root. Okay, so this is basically the result of this integral, but now, as we said, we have to calculate the integral of 1 over basically z to the power of 4 plus 1 dz 0 plus infinity. And we know that this integral is given by 1 half the integral of from minus infinity to plus infinity of the same function. Since this function is symmetrical with respect to the y-axis. Okay, so as we have this integral to calculate, we can consider the limit of this integral as r goes to infinity. So the idea here is to again consider this integral over C with r approaching plus infinity. But as we said, this integral can be written as the sum of the two integrals above. And here basically we can consider the fact that this integral as r goes to infinity goes to 0, so this integral goes to 0, so we end up with just this integral. But if we consider r approaching plus infinity, we end up basically with our integral, which is this one, which is 2 times the integral that we were given at the beginning. Okay, and we know that the fact that we are considering the limit doesn't change the fact that this integral from the residual theorem, as we said, is pi over 2 under square root. So here basically we have to consider this equation, and from because of this we can write we basically can write that our integral from 0 to plus infinity of 1 over x or x raised to the power of 4 plus 1 dx is, as we said, pi over 2 times 2 under square root. So this is the final result, and we basically reached the result thanks to the residual theorem. So the idea in this calculations is to consider a path C, which can be split into these two paths, and then consider the limit for which r approaches plus infinity. Here this integral goes to 0, and this integral basically becomes this integral, which is 2 times the original integral. But we know that this integral because of the residual theorem is this, so we end up with this result.